Hi everyone, welcome to our video on carbon-13 NMR. Today we'll be going over the concept behind carbon-13 NMR, which you'll find is actually very similar to our proton NMR video. And we'll also be going over some of the major terms, again, which are very similar to the process of proton NMR. So we're going to start by going over the carbon-13 NMR spectrum, as well as the concept behind it. And you'll find actually that the concept behind carbon-13 NMR is actually very similar to the concept behind proton NMR. And if you remember in proton NMR, we focused a lot on the spin of the nuclei and the magnetic environment for those nuclei and what types of magnetic environments they feel. And in this case, it's the same thing, except now we're really focusing instead on the proton, we're instead focusing on the carbon of the molecule of interest. And something important to keep in mind for NMR spectroscopy in general is that only nuclei with an odd number of protons and neutrons can be measured through NMR. And the reason for that is that NMR can actually measure any molecule that has a spin quantum number that does not equal to 0. And the only way you can have a spin quantum number that does not equal to 0 is if you have a nuclei with an odd number of protons and neutrons. So that's why we measure things like H1 NMR and carbon-13 NMR as opposed to carbon-12, for example. So looking here at the NMR spectrum, I just want to highlight some of the things that are pretty similar / different from the proton NMR spectrum. So the first thing I want to highlight that's the same is that the axes are the same. We have ppm on the x-axis, measuring the chemical shift. Here we have the intensity of the signal. And again, we have these signals being registered here. The TMS serves again as our reference point, so you'll always see it at 0 ppm. And something that's different about carbon-13 is that the x-axis, the chemical shift, actually ranges from 0 to around 200 to 250 ppm, as opposed to in proton NMR, it actually ranges only from about 0 to 10, so it's a lot more narrow. And in carbon-13 NMR, of course, our goal, as with all modes of spectroscopy, is to determine, to get information about the molecular structure. And we consider in the same 4 things that we considered in proton NMR, except this time we consider them in the context of carbon. So here we look at carbon equivalency instead of proton or hydrogen equivalency. We look at the chemical shift, we look at integration, which is the ratio of equivalent carbons this time as opposed to protons, and then we also look at signal splitting and spin-spin coupling to get some information as well. Again, carbon equivalency, or similar to proton equivalency, is important in determining the number of signals. So however many non-equivalent carbons you have is equal to however many signals that you should see. So if we're looking at a molecule like ethanol, for example, and this diagram is great because it actually already labels it for us, we see that we have carbon 1 and we have carbon 2. And carbon 1 and carbon 2 are considered non-equivalent to each other because they feel different magnetic environments, and so as a result, they are non-equivalent. And with these 2 carbons being non-equivalent, this translates to having 2 different signals that are registered on the NMR spectrum. Next thing we're going to look at is chemical shift, and similar to proton NMR, chemical shift gives us information about the position of the signals along the x-axis. And what's important in carbon NMR is that these chemical shift is very much affected by things like pi electron clouds and electronegative atoms. And specifically, pi electron clouds and electronegative atoms cause something called deshielding. And if you remember, deshielding refers to how the electrons kind of move away from the carbon and really kind of don't really surround it or protect it as much anymore because they're being pulled aside by maybe a really electronegative atom, or they're being delocalized due to these pi electron clouds, due to some kind of double bond that it has with something else. Something to keep in mind is generally pi electron clouds and electronegativity can cause deshielding, but know that pi electron clouds can also cause shielding as well. It kind of can oscillate. And similar to, again, proton NMR, deshielding occurs, and when you have deshielding on a carbon, this means that there is a greater chemical shift. If you look at carbon 1 here, carbon 1 is attached directly to a very, very electronegative atom, oxygen, and as a result, the carbon 1 here is very pretty heavily de-shielded, as opposed to carbon-2, which is further away from this oxygen. It doesn't quite feel the oxygen's tugging away of its electrons as much as carbon-1 would. And so because of that, carbon-1 is more heavily de-shielded than carbon-2, and as a result, it has a greater chemical shift, meaning it moves more downfield. So its chemical shift is around, I say 59, or actually 58, it says here, as opposed to carbon-2, which feels a chemical shift of about 18, which is much smaller. The next thing we're going to talk about is integration. I'm not going to go into too much detail here because integration is actually really not that helpful for carbon NMR. And the reason for that is because integration has a lot to do with relaxation time from excited state to ground state, and carbon tends to take a really long time to go from an excited state to a relaxed state. So integration doesn't really give us that much information in carbon NMR, but it does kind of give us information similar to the proton NMR. It tells us the number of carbons per signal, it gives us information about the carbon intensity, but again, not so useful for carbon-13 NMR, and I'm not even going to really go over it because it's not really emphasized in your lectures. So the last thing I do want to go over, however, is signal splitting, which is super important. And so if you remember from lecture, from class, there's a process called spin-spin coupling, and this is when the atom nucleus that you're looking at feels multiple magnetic environments. When you have this type of process, this causes signal splitting. And something to remember is that only carbon-13 can couple. So some important rules to keep in mind is that, again, we're counting the number of bonds in order to determine which ones are considered neighbors. So if you remember in proton NMR, we counted 3 sigma bonds away, whereas in carbon NMR, we actually only count 1 sigma bond. So really, it's even easier for us now. We just look at carbon and then the hydrogens that are attached to it, and that's all that matters. So for example, let's look again at ethanol here. In carbon NMR, our focus is, of course, on the carbon, and we're really concerned only with the things that are, the hydrogens that are only a sigma bond away from the carbon. So we're looking at this hydrogen, and this hydrogen, and that's all we care about. We don't really need to look at anything else. And if you remember in proton NMR, we talked about pi bonds being free spacers that you can kind of skip over and count, don't have to count. We don't have that process here. So these do matter in carbon NMR. And then the last thing, of course, the number of lines that the signal splits into follows the n+1 rule. So again, let's look at this carbon. And this carbon has 1, 2, 3 hydrogens that are attached to it. So as a result, it will actually split into 3 + 1, which is 4 lines in that one signal. Whereas this carbon here has 1, 2 hydrogens that are attached to it, so 2 + 1 is 3. So this carbon will actually split into 3 lines in its signal. But you might be looking at this spectrum here and wondering, well, I only see 1 line here and 1 line here. I don't see any splitting at all. And the reason for that is that this is actually just a convention in organic chemistry. There's a process called broadband decoupling. And this basically converts all the split signals into singlets, and it's kind of just a way of making it easier to read. So that's how we can see so clearly that there's 2 signals here. So I have here 2 sample molecules. We're going to answer the question that is asked here, and it says, how many decoupled signals are expected in the carbon NMR for the following molecules? So let's take a look here, and again, we want to count how many carbons are equivalent to each other and how many groups of non-equivalent carbons we have. So I'm going to go through and kind of just indicate the carbons that are in the molecule so you can kind of see this better. This one right here. So here's this carbon. Let's start here. We're actually going to consider this as 1 signal here. It's not equivalent to anything else in the molecule. Let's go to this carbon over here, the one I just deleted. This carbon over here is attached to 3 hydrogens and an oxygen. And so we have 1 CH3 carbon, but there's no other carbons in the molecule that are also CH3 carbons. So this is actually going to be considered another carbon that's not equivalent to anything else in the molecule. So I'm going to call it B. Let's take a look at this carbon. So I'm going to label this as C because it's also not equivalent to anything else in the molecule. Now let's go ahead and take a look at these 4 carbons here. Particularly, let's look at this one and this one. So these 2 are actually equivalent because they are connected in the same way to carbon A. If you remember, I mentioned this in the proton NMR video, but it's helpful to look for things like symmetry to help you figure out which atoms are equivalent to each other. And so these 2 are actually equivalent. So I'm going to label this as D and D. And then similarly, these 2 are equivalent to each other. So if we were to determine how many decoupled signals, again, remember decoupling means we don't have them split anymore, how many decoupled signals we would expect to see, we would expect to see 1, 2, 3, 4, 5 signals in the carbon NMR spectrum for this molecule. Let's go ahead and take a look at this one now. So I'm going to go a little bit faster. So here we have 1 carbon. This is not similar or equivalent to anything else in the molecule. So here I'm going to label this as A. Here we have another CH3 similar to the one over here. This is also not equivalent to anything else because there's no other carbon that also is attached to 3 hydrogens. Then we have another one here. I'm going to label this C, also not equivalent to anything else. And again, you might be tempted to maybe look at the benzene and make these 2 equivalents here and here, but in fact they are not. So this will be D, this will be E, this will be F, and this will be G. So I kind of labeled that out of order. Sorry about that. But here we have A, B, C, D, E, F, G. So we'll have 7 signals being registered here. Actually, excuse me, 8. There's one more right here. GH. So we'll have 8 signals. So thank you for listening, guys.